Hey everyone, so what we want to do here is establish the formulas for gravitational potential energy and elastic potential energy. We looked at this and explored it in class today, but I want to go through the derivation and where those come from. So what we can see is that the gravitational potential energy, we'll write it as U sub g, is the energy stored in an object due to its location, and technically it's the energy stored in the gravitational field. So once the energy is in the gravitational field, that energy doesn't want to stay in the gravitational field. It wants to get rid of that energy, so the object changes its potential energy into some other type of form. So the way you can solve for this is you can say that du is equal to the integral of negative force dotted with displacement. And in the case of using the force of gravity, we can put mg in for our force. So if we integrate here, we can have that du turns into negative mg dotted with the displacement. And we'll take that from no displacement to our final displacement. And let's just call that a displacement of y, since the object may be up here and have started at the ground. So the object has gone through a displacement, has moved up a delta y there. So if I integrate both sides, du just becomes u. On the other side, mg's are constant, and I have to integrate dr. And dr just becomes r, and you evaluate that between the start and end point. So it's going to be times your delta y. Of course, plus a constant, and that constant there is going to be our initial energy due to some reference point. And this is the nice thing about gravitational potential energy. It means we pick the zero line. So what that means is that in a situation, in any problem, you pick where you want height to be zero. So you pick 0 where the box is at the ground, and your displacements are measured from that zero line. It can be wherever you'd like that to be. If I put the zero line up here at the top of the page, then technically I have a negative displacement. And if I have a negative displacement, then I'll have negative amounts of gravitational potential energy to start with. Is that necessary in all problems? No, but you want to make sure that you do establish where the zero line is. If I said that the zero line was right at the object, then I would have no displacement from that zero line, and I would have no gravitational potential energy. In a problem, it's the easiest thing for us to do is put the zero line usually at the bottom of our hills or the bottom of our scenarios. We'll take the gravitational potential energy of this iPad to be 0 on the table, and as I lift it off the table, I'm increasing the y displacement and increasing the amount of gravitational potential energy. But if the iPad was going to fall to the floor, then maybe I'd make the problem have the zero line at the floor. The point is, pick the zero line that's going to make your problem the easiest for you. And you want to make sure that you don't change the zero line during a problem. Once you pick a zero line for your scenario, you've got to keep that zero line the entire time. Really, we can have our gravitational potential energy end up looking like that. So the change in gravitational potential is Ug, and it's equal to mg delta y. And since we're talking about an up and down vertical displacement, a lot of times you'll see this written as m times g times h, the height above your zero line. Let's check the units on that. Okay, so looking at our units here, mass is measured in kilograms, gravitational acceleration is meters per second squared, and a displacement is just meters. We can see that mass times acceleration we know is a newton in terms of force, multiplied by our displacement. A newton meter turns into a joule. Gravitational potential energy is measured in joules, just like work done or kinetic energy as well. We can also have potential energy in the form of elastic potential energy with big U sub s. So the energy is stored in a spring, or sometimes you'll see it as energy with EL for elastic energy, but I think US is the way that you'll see it on the AP sheet. This is the energy stored in a spring when that spring is compressed or stretched from, you guessed it, our own 0 point. And the 0 point for a spring is pretty easy. You want to take that 0 point to be when there is no stress or compression in the spring, that relaxed length for a spring. So we can use the same setup we had last time and say that du is equal to the negative integral of f dot dr, and this time this force is a spring force. So we're going to pull all constants out of our integration here, and we're going to pull out the negative k, and you get the integral of x dx. X dx becomes 1/2 kx squared plus the initial energy there. So the initial energy, remember, is the energy when there is no stress or compression. So just like we had a 0 line for height energy, we can also have a 0 line for potential energy in a stretch. If we check the units here, we know that the spring constant is measured in newtons per meter, the amount of force it takes to stretch a spring over 1 meter. The distance there is the length of compression or stretch, so we square that and we get square meters. Getting rid of one of those meters gives us a newton meter again, which comes out to a joule. So elastic potential energy, gravitational potential energy, work, or kinetic energy all have units of joules. Which brings us to this concept that we saw in our demonstrations today of this idea that we can conserve mechanical energy. So that when we look at a scenario, we want to see that all the energy we start with in a problem, we should end with in a problem as long as we're dealing with conservative forces. So the first thing we can say is, let's establish the work-energy theorem, that the net work done equals the change in kinetic energy. And the net work done really can be a combination of external work done by applied forces, it can be work done by non-conservative forces like friction, and it can also be the work done by conservative forces. We know that from what we talked about last time, the work done by conservative forces always tries to decrease our potential energy. So I can move that minus sign to either side. In this case, I'm going to move it to the left side for work done by conservative forces. In a scenario, let's say that there is no external force and that there is no conservative forces. That way, we can say that the total energy of the system must add up to 0. So if I put in work done by external and work by non-conservative forces, adding them up to be 0, I can see that I can rearrange this and find out that the change in kinetic energy in for my net work, and I'll put this in for the work done by conservative forces. These two are going to cross out to 0, and what I'm going to get is a change in kinetic energy plus a change in potential energy equals 0. And we take any change in energy from its final point to its initial point. So what you can say here is that the initial energy of a system must equal its final energy of a system. And when we do that, we pick two locations. All we care about for work done by conservative forces is the energy at one location at your start point and energy at the ending location. That is it. We don't care how the object gets from one place to another. We just care that the energy has changed from one point to the end. So the total energy of a system will not change. So when you do a problem, what I recommend is you kind of come up with this score sheet. You've got on the left side all the energy you could have at the beginning of a problem, and at the end you have all the energy you could have at the end of a problem. So in the beginning of a problem, you could end up with some kinetic energy based on speed. You could have some gravitational potential energy based on a height. You could have some spring energy based on initial stretch. There might be friction in a problem. And if that is, that means we're going to deal with work done by non-conservative forces. Or maybe there's a person pouring energy into the system. That'd be a work done by external forces. Most of the time, it'd be easier if you don't worry about applied forces and not work done by friction, so those really won't apply to you each time. And all that starting energy should equal all the energy you have here on the back end. So the kinetic energy plus the gravitational energy plus the spring energy at the end must equal everything we started with at the very beginning. So we looked at an energy schema in class, and I think we started into the LOLs, And an LOL is really just a bar graph for organizing all your energy in a problem. So the energy bar graphs keep track of the amounts of energy we have at certain locations. You picked point A and point B, and we look at how the energy changes as it goes from one point to another. So in the beginning, there's our scorecard. Do we have speed in the beginning? Do we have gravitational energy in the beginning? Do we have spring energy in the beginning? That's what we want to focus on in each scenario. Is there any friction involved? Is there any work done by external forces? So if there is, you can fill up these bar graphs. If there isn't any energy, you can leave it blank. Is energy, you can fill up these bar graphs and show me a qualitative way of how much energy you have. If there isn't any energy, you don't have to draw any bar graphs whatsoever. Or an easy way to establish that is you could say that there is no gravitational energy in this problem. There's no work by friction. There's no external forces. And that kind of eliminates any of the energies you need to write in a problem. So what we're going to focus on tomorrow in class is this idea of energy conservation and energy transfers from one place to another. You will be playing around with the energy skate park, so I'll give you a little preview of that right now. So if we look at the energy skate park here, what I can see is that I have a skater going back and forth in this little half pipe. And I can tell that he's got different types of energy based on just his motion. It looks like at the bottom here, he's got a lot of kinetic energy, and at the top, he's got more height. And since he's got height, I would say that he's got gravitational potential energy based on a 0 point. And I'm going to make that 0 point the bottom of our track. So if I wanted to focus on two locations here, I'll focus on the top part of our ride. So I paused him up here at the top, and if I come over to my scorecard, I want to say, okay, what kinds of energy do I have? Well, at the top, he's not moving. So I would say there's no kinetic energy. I would also say that there is some height energy. So I can give myself a bar here for gravitational potential energy. There's no spring involved. So there's no elastic energy. There's no friction. I'm not going to put in any external forces. I'm not going to give him a push. So I've established my scorecard on the left. I've got gravitational potential energy, but I don't have any other forms of energy. In my system here, I want to define who's in the system. And the things in the system, you could say, are the track. You could say the skater. So those are the objects that I'm going to focus on. I'm going to focus on the earth, the track, and the skater. Right now, there's gravitational energy. So it means the energy is sitting here inside the earth. If I go to my second scenario, let's take the second point to be when the skater reaches the bottom. So I have the gravitational energy at the top, and right here at the bottom, he's moving pretty quickly. So if I go back to my scorecard, at the bottom of the track, I'd say he's got kinetic energy now. He's moving as fast as possible. He's lost all gravitational height energy, and still there's no spring involved. So what I can do in my flow chart here is say that, all right, I had 5 units of gravitational energy in the beginning. If you look at point B, it looks like I have 5 units of kinetic energy at the end. So energy left the earth and went into the skater. So energy transferred because gravity did positive work and decreased the skater's potential energy and transformed that into kinetic energy. So this is how we can write the scorecard. And the whole point of writing the scorecard now is that I can write a formula based on my problem. I can say that at position A, I have gravitational energy. And that must equal my energy at position B. So my energy at position B is kinetic energy. So I can say the gravitational energy in the beginning turns into my final kinetic energy at the end. And we have formulas for those now, so I could solve for heights or speeds, depending on whatever is given to you in a problem. So when we look at a scenario, we're trying to write down what energies objects have at different locations. Once we write an LOL, or an energy bar graph, we'll be able to establish an equation for our problem just based on energies at 2 locations.